So we're going to continue with the pretest, and we're going to start by looking at number 32. If you look at 32, we have a crate being pushed up an incline, and they want to know what is the change in potential energy. Where's the important thing? It doesn't really matter how far along the incline they go. The change in potential energy is just their change in height. So we just take our gravitational potential energy, and it's mgh, and so we'll find the difference in those two heights, and it's 5 meters. And then you plug everything in, and you should get the right answer. So that one was fairly easy. But just finding the difference in those heights, that's the tricky part. Okay, so we have a projectile. So it's alright, it's being launched, and it has an initial x velocity of 30 meters per second and an initial y velocity of 40 meters per second. And they want to know what is its kinetic energy when it reaches its highest point. Now here you have to be careful, because you remember when it reaches its highest point, its y velocity is 0, but it still has that x velocity of 30 meters per second. So the kinetic energy that we're worried about is just that one there. So we go 1/2 mv squared for our kinetic energy. And so it's 2 kilograms. 1/2 of that, 10, times the velocity squared. So that's how you get the 900 joules. Okay, so we have a skier leaving the top of a slope. He's got a velocity of 5 meters per second. So here he is skiing down the slope. And he's going to go down, and down at the bottom of the slope, he's going to have a velocity of 13 meters per second. And they want to know how high is the slope. Okay, so again, we're going to ask ourselves the questions. Is it moving? Yes, so it has kinetic energy. Is it above ground? Yes, so it has gravitational potential energy. Is it stretched or compressed? No, it's not even up there. So down at the bottom of the hill, it's just got kinetic energy. And our total energy at the top is equal to our total energy at the bottom. So we're going to take that and we know we have kinetic energy plus gravitational potential energy at the top is equal to the kinetic energy at the bottom. Okay, so 1/2 mv squared plus mgh is equal to 1/2 mv squared. Notice in the problem, they didn't give us the mass of our skier. Well, look, all of our terms here have mass in them. So the mass term can cancel out. It goes to 0. If this just gives you conniptions and it doesn't work, you can just randomly assign the skier a mass. And so you can say, okay, the skier's mass is 100 kilograms, because that's kind of a reasonable mass for a person. But remember, we're talking here about the top, okay? So we're going to use the velocity at the top. So the velocity at the top is 5 squared plus 9.8, and then we're solving for h, so we're just going to leave that as a variable, equals 1/2 the velocity at the bottom squared. And then solving for h, you should get your correct answer. Okay, so this is a power problem. This is 47 in your pretest. And they tell us that the power is 1440 watts. So don't get confused. That's the power unit. That's not work. And we're going to lift a crate that's 207 kilograms from the ground to 2.75 meters above the floor. Okay, So you could do work equals force times distance, because power is your work divided by your time. It's also your change in energy divided by your time. And in this case, our change in energy, we're changing our kinetic energy, or our potential energy. So you could find the potential energy of the crate. The work, if we were going to do force times distance, the force we would use would be the weight of the crate, because you have to lift against that weight of the crate to get it up there at the top. So our 1440 is equal to, I'm going to do change in energy. Okay, so our mass, 207 times G, 9.8. Hey, guess what? That term right there, that's its weight. So either way, we're doing the same work, times 2.75 divided by T. And remember, when we have our variable on the bottom, that's oftentimes when we make our mistakes. So if you put the other side over 1, then you see it's a proportion. You cross multiply and divide, and you can get the correct answer. Now this one, 48, I put in just because it shows the relationship between the energy used in a light bulb and the potential energy that we get in objects. Light bulbs actually use a lot of energy. So this 0.1 kilowatts, okay, kilo means 1,000. So we have a 100-watt light bulb, and that's the power. And we're going to run it for 1 minute. So what do we have to do that 1 minute? Convert it to seconds. So our power is equal to our change in energy over time, or our work divided by time. And the reason why I chose energy is because it gave us vertical distance, so I'm going to find its gravitational potential energy just like I did in the previous one. So 100 is equal to the change in energy divided by 60, so our change in energy is 6,000 joules. And that's going to equal our gravitational potential energy, which is mgh. So 6,000 joules is equal to 1 times 9.8 times h. So you can see that when I take 6,000 and divide by 9.8, that's a huge distance. And that's just to power your 100-watt light bulb for 1 minute. So that's how much potential energy it uses. So our electrical energy is often a lot bigger than our gravitational or kinetic energies. Okay, I'm just going to outline this one. This one's not hard. It says determine the work done by the force. So work equals force times distance. Okay, notice we have force and distance. So what gets us to multiply those? That's finding the area. So the area between the line here and our x-axis. So just find the area, split this up into little shapes, and then add them up, and that'll give you your total work. So that one's fairly easy. This one is a little bit trickier because our crate is not only changing its gravitational potential energy because it's moving up, it is also changing its kinetic energy. Okay, so when we find out how much work was done, we need to add those two energies together. So since you have an acceleration, this one's a little bit more involved, you need to find your final velocity so that you can get its new kinetic energy. And then you know the height so you can find the gravitational potential energy.